Okay, so now we go to the next speaker, John and Pitt.
That's all right. Okay, so I'm Jordan Pitt from the University of Adelaide, doing these model predictions of overwash extent into the marginal ice zone, working with these great people, and I'm supported by the ARC. Okay, so we're going to the marginal ice zone. Here's what it looks like. We have our fragmented ice cover with these floes separated by water or a slurry of ice, and we're really interested in the flow motions. And I guess coming from a wave background, which some people in the audience are from as well, we're very interested in the propagation of waves from the open ocean into the marginal ice zone, which we can see to the right of this image here. So when we have floating bodies and waves, we can get overwash. So this is where we get flows of water across the surface of the bodies due to the coupled flow and wave motions. So we have two experiments here, one on the left, waves came in from the left, traveled right, and we can see a bit of overwash here on the left disk in the left example, and then a lot of overwash here on the right. So these overwash is very sensitive to the flow and the wave conditions, as we can see here, and we're trying to understand this process. In particular, we're trying to understand it because we know that it has a role in the interaction of ice and the waves. So overwash is going to be a mechanism for dissipation of the wave energy. It takes wave energy to generate it, and also it's going to be a mechanism possibly, since it's depositing water on top of our flows and possibly even ice crystals, for growth and melting of the ice floes as well. So overwash is very common in the lab, to the point where people built little barriers on their flows to try and stop overwash from occurring, sometimes successfully, and even under very non-steep conditions. So, you know, it doesn't have to be very steep at all to generate overwash, especially because ice is very close to the density of water. However, there isn't really any systematic field work, which isn't a criticism. It's going to be a very hard region to study where overwash is occurring. It's really right at the fringes of your field of ice, as we'll see later in the presentation. So our goal really is to take what we know from the lab, do some modeling, and try and provide the extent of overwash into fields of ice in the marginal ice zone to hopefully inspire some people to maybe go there, but also maybe to better understand the dynamics of the ice right where the overwash is occurring in terms of growth and melting. Okay, so this is our model. Looks much simpler, but this is just communicating that our overwash of many flows needs an overwash of a single flow, essentially. So we're going to start with a single flow model and then go to multiple flows. So you're going to give me some flow. My model's 1D, so we'll just have a length and a thickness. Yes. And it has some dynamic properties, in particular the density, the Young's modulus, and the Poisson ratio, since we will assume that it's elastic, as we'll see. Okay, and then I want to send in some waves. In particular, I want to send in a spectrum of waves, since this is how we describe waves in the ocean. We have some random wave field, and we describe it by a spectrum, which I'm going to go into a bit more detail here, just because maybe some people aren't familiar. So our spectrum describes the distribution of energy over the random wave field into their frequency components. And in particular, this spectrum has a significant wave height of 0.02. Significant wave height is kind of a loose bound on the heights of waves in our random wave signal. And then a peak period, which is the period at which we get the peak in the spectrum. So it's this dashed line. I've drawn it as frequency, but it's the same as this corresponds. Okay, and I can actually plot, of course, the amplitudes and the frequencies for these components. So I've done that here on the right as an example. We have low frequency over here corresponding with low amplitude in the spectrum signal. As frequency increases, our amplitude increases, and then it starts to decrease according to the spectrum. This is actually a description of an ensemble of random waves where each realization is given by a combination of random frequency components of these components with a phase difference. And we get something like this for a typical realization where the significant wave height is a loose bound, as I said, on the heights of waves in our signal. Okay, so this is our incoming wave. And then we need to, in particular, describe the spectra of the coupled flow and wave motions. In particular, since my model's 1D, at the left and right edges of my flow, I'm going to describe an ensemble of waves coupled to the flow's motion to be able to determine overwashing, which I call SL to denote L, left, and SR to denote right. To do that, we need a coupled flow and wave model, which is what we have here. So this is a schematic. My flow is of length D, thickness H. Since the density is so close to water, the freeboard's quite small, which is FB. And my water is capital H deep, although it's going to be pretty much infinitely deep for my purposes today. And then we're going to use elastic thin plate theory for the ice and linear potential flow theory for the water. Solving these equations, you can get out the reflection, transmission, and the flow motion coefficients, and in particular, combine them to get these three spectra of interest using this method here of Luke. Okay, so I've drawn the spectra with the point that they're relative to. So the incoming wave is relative to the still water line. My left spectrum is relative to the flow's motion, so it's actually on the flow and it moves with it. And it's given by this expression here, which just depends on the reflection coefficient R, the flow left coefficient FL, and the incoming wave spectra. Likewise, on the right, my right spectra depends on the transmission coefficient T and my flow right motion coefficient FR and the incoming spectra. So now I have my three spectra, and I can use those to determine a frequency of overwashing, kind of using some classical random wave theory, in particular this FOW, which you will calculate. Okay, so this is a kind of classical theory of Rice, where you give me some random waves and I can tell you the mean time between waves above a certain height. And in particular, I'm going to be interested in the height of the freeboard plus some small tolerance. So I want waves that are above my freeboard or the flow with some small tolerance, just because I don't care if it's, I'm not interested in overwashing of like 10 to the negative 10, right? Like it doesn't really matter. Well, that's like numerical. So we're trying to avoid that with this tolerance. Okay, and this is the expression here. It's the mean time between waves above the freeboard, i.e. the mean time between overwashing waves, is given by this expression here on the right, which just depends on our spectral moments of the spectra that we have. So at the left edge, it's SL, and at the right edge, it's SR. And this is the definition of our spectral moments. So now we have the mean period of the incoming wave, the mean time between overwash events at the left edge and at the right edge. And we compare those to get a frequency of overwashing, which is given here. And we take the maximum just because we don't care whether it's the left or the right that is overwashing. Although it tends to be the left much more, which if you recall, the expression kind of indicates that, yeah, that kind of one factor in there, whereas transmission will tend to be below 1. Okay. And then we've just set a tolerance in our frequency of overwashing to get a condition for overwash. So we say the flow is overwashing if our frequency of overwash is above this tolerance, which we choose to be 0.05, which corresponds to an overwash period, an overwash event at least once every 20 mean wave periods, I should say. So it's quite long, but still kind of significant. And if it's below that, then we don't care. We just think it's overwashing too infrequently to care. Although I guess we can also pull out even more information and get some kind of distribution of frequencies and even possibly heights as well from our spectra at the left and right edge. Okay. So that's kind of an ensemble description. I kind of also wanted to show a realization comparison. So I actually didn't put the frequency of overwashing in this event, but using this frequency of overwashing, I have calculated the frequency of overwashing for the spectra that's incoming, which is given by this peak period of 6 and a significant wave height of 0.2. And it says that overwash isn't predicted according to this tolerance. And so now we can look at a video of what that actually looks like. Maybe. Really? Will it cancel me out? Okay, gave me the things I want. Sorry. We okay? yeah, so I mean, overwash isn't happening, so that's good. It is possible that you have one realization that is very statistically rare, but could generate an overwash event maybe over the signal. Okay, likewise, we can use an ensemble approach and find an example where it is overwashing. And this is that example here, and it's much more dramatic. I've picked a dramatic example, I guess. And we have, okay, just a shallow water wave equation on top. So the flow and the wave motions are just a linear theory. And then we just use the shallow water wave equation when the water gets above the height, which tends to flow off pretty quickly just because of the pitch the plate is at in this example. And we're back. Yeah. Okay. So it seems to work, which is good, kind of encouraging. Okay, so now what we want to do is go to our array of flows and use the MIS properties. In particular, we're thinking like these kind of large scale properties you would get in these larger scale models, in particular like a concentration, a flow size distribution, and we're just going to use a uniform thickness, and that's mainly for simplicity, but you could imagine doing a flow thickness distribution in there as well. And then, since we know the array of flows according to these MIS properties, in some realization sense, we need also an attenuation model which tells me what my incoming spectra is to all those flows so that I can determine if they're overwashing. So that's due to a combination of the ensemble of scattering caused by the flow size distribution, as well as an empirical model for attenuation, that kind of Malin one with power of 2 and a power of 4 that he published. In particular, it doesn't have dissipation due to overwash, which is, so we're kind of we're overestimating it, I guess, is the caveat there. Okay, so how our spectra evolution works is just, again, just kind of what I said in words. We want some incoming wave spectra to our marginal ice zone, or this array of flows, and then to know what the spectra is incoming to subsequent flows, as we see there. So then we have, each flow has an incoming spectra. We can determine if it's overwashing or not, and then we can start defining a distance of the extent of overwash into this array of flows. So good, great, done. But of course, you have to check that this makes sense or works against at least laboratory experiments. So that's what we've done here. We have our wave maker here on the left. It generated irregular rightward propagating waves, and they interacted with this array of wooden disks, which are the brown circles. You'll notice that the maximum depth is 3 in the direction of wave propagation, although there are 2 examples as well. And these were recorded by cameras situated above the disks, which are these red squares, which had this field of view, which is the red box around them, allowing us to observe overwash during the experiment. Any waves that transmit are then dissipated by this beach, and there wasn't really any measured interaction of reflected waves from the beach back into the array. So there was a series of tests with different regular spectra. And for each of those, I know the spectra, I know my array of disks, I can make a prediction of the extent of overwash. So this is what this plot represents. This is our model predictions. Each point in this plot has a significant wave height and a peak period as an incoming wave spectrum. And I color that according to the prediction of the overwash extent measured by the number of disks overwashed. So in dark blue, I have no disks overwashed, up to this kind of yellow color where I have all 3 disks overwashed. The interesting things to note are when we have very low periods, we have high reflection of waves. This increases the wave heights in front of that initial disk, which means that we don't need much significant wave height at all to overwash the first. In fact, you kind of limit down to the half the freeboard, essentially, because you get a doubling effect for very high reflection, essentially. But since most wave energy is reflected, it's not transmitted, and so you need a lot more significant wave height to overwash subsequent disks, even though there is high reflection. Conversely, for very long periods, we don't get much reflection, so the wave heights in front of that initial disk aren't very elevated, so you'd need more significant wave height to overwash it. However, since most wave energy is transmitted, it's a bit easier to go to the second and any subsequent disks in terms of overwashing. Okay. So we had 3 irregular wave experiments. 2 of those had 1 disk overwashing, just that first disk. And these sit right in that blue region, the light blue one, corresponding to 1 disk overwashing. So pretty happy about that. And then there was another experiment where all 3 disks overwashed, and that's this experiment here. We also did do some regular wave tests, and there was a lot more regular wave tests, so you can get a lot more points in there. But since I'm just talking about irregular waves today, I just focused on this one. And that's, yeah, we'll get to that. Okay, so great. Now we want to go to the marginal ice zone. Okay, so we had our ice concentration. This is what the South African Argyll House 2 observed that Alberta was talking about on its 2017 July voyage into the winter Antarctic marginal ice zone. So it traveled down south along this path and looped back around on itself here. So we have here the marginal ice zone properties, the ice concentration, have some thicknesses, some assumed thicknesses, and indeed we have a flow size distribution that Alberta worked on inside this marginal ice zone that we can use as well. And we also have the wave properties coming into the marginal ice zone. However, we can only do 1D models, so we're just going to do a series of lines which are all parallel and traveling in the mean wave direction. And they start up north and they travel into the marginal ice zone, and we stop drawing them when we stop predicting overwash. So that creates this region here. I guess the first thing to point out is that, yes, I'm saying that the open ocean is overwashing. What I'm really trying to communicate here is if you took a flow from this marginal ice zone and put it in this hatched region, you would get overwashing, essentially. And indeed, we don't know, there might be some ice that's in there that we can't see with a satellite, for instance. Okay, the other thing to note is that the overwash region is really confined to the very edge of our marginal ice zone. It really doesn't penetrate very far at all. And this explains the kind of seeming paradox between the prevalence in the lab and the lack of systematic studies in the field, essentially because, you know, lab work occurs over a much smaller scale. They can't get to these kind of lengths where it just stops mattering, essentially. Yeah, although we did find that it's a very persistent feature. So although maybe it doesn't penetrate up into these very high ice concentrations, even for very small waves, you'll get some overwash. Now, the extent may vary, but it's probably a factor in the evolution of your edge of your marginal ice zone, amongst other things. Okay, so I'm going to finish with some good news, I guess. This is in a paper that's been accepted since I arrived. So I guess they heard I was here and they had to publish. So that's good. I also have some fun things at the end if you want to indulge me. I guess first as well, I'll just do a little bit of a shameless plug. I am hosting a workshop on the mathematics of sea ice, yeah, but also ice sheets. We're trying to combine and see what the kind of common links are in these communities, and that'll be in November. So if you're looking to escape the winter in Europe, I guess this is a good option. And we are doing some hybrid as well, and registration closes coming up, so getting quick. Yeah, I wanted to thank the organizers a lot for their organizing. I know it's a lot of work, much more for them than what I've been doing for mine. And I kind of wanted to highlight what's interesting about conferences and getting together in person. And so Danny's Dumont's talk was very interesting, and he showed a dispersion relationship. And Luke was mentioning some of my work that I've been doing, which was essentially looking at breaking up a block of ice. So you have your ice. Yeah, actually, I'm not going to get that. And looking kind of at the homogenized limit, where you break up your ice so small that it almost doesn't matter, right? And you might think, well, maybe this just goes to a mass-loaded system. But in the model, if these little chunks of ice are a bit elastic, at least over the small region in which they're solid, then you actually get something different, which is what Luke was showing. And what he doesn't know, and maybe he doesn't want me to show today, but I worked on briefly on the weekend just to see, because it inspired me to do so, was something like this. So if you plot your dispersion relationship, your frequency, and your wave number, we have our mass loaded. The colors are terrible, sorry. We have our mass loaded up the top. We have, in yellow is water, just the water dispersion relationship, and then blue is flexural. Our purple, which you can barely see, is this kind of homogenized limit of these small chunks of elastic bodies, but they're disconnected. And that actually starts for very low frequencies on the mass loaded system, but there's some kind of transition to the kind of almost the water, which I find very strange. Also, it's kind of interesting as well, because I was here, I thought I might as well plot the attenuation rate, although I take Sasha's point that maybe the attenuation rate is not a well-formulated question. And we have our red is our mass-loaded system, and then our purple is the small flow limit, and blue is our flexural wave, and then we have the dashed line, which is just a power of 3. And we can see that purple kind of looks more like a power of 3 than any of those two. Just something exciting, interesting, and something that can only happen because we were here, and I wanted to, start with something interesting and end. Thanks.
I wonder if I could just do something I don't normally do, which is just read something from an old paper I wrote a very long time ago, which actually bears out a lot of the things you've said. Mm-hmm. This is, I'm sure you've seen it. Well, I hope you've seen it.
Yeah.
It's a paper I did in 1980 with a colleague of mine from Cambridge. And it talks about, if I can just find the beginning, from the ice cover, it's the Bering Sea. Mm-hmm. The water depth is about 100 meters where we were. From the air, the ice cover could be divided into 3 distinct zones made up of floes of quite different character. The edge zone, which stretched from the ice edge some 5 kilometers into the pack, the transition zone, which stretched a further 25 kilometers, and the interior zone. This zonal structure has been observed earlier in the field trip and was the reason behind our choice of flow separation. The edge zone was made up of floes which had been buffeted together in waves of sufficient intensity to ridge, raft, and fracture the ice. And then it goes on and talks about the flows further in. So the conversations I've had with Luke and now you mm-hmm. probably suggest that edge zone, which was very wild, I mean, it was would have been quite difficult to work in, I think, although something I look at further in the paper worries me that I actually did work in that edge zone. The attenuation was very significant. Yep. It was much higher at short frequencies. Yep. I fitted a curve over 80 kilometers, but if you look at the short frequencies, the high frequencies, short period waves, you'll see that the gradient was much steeper in that first 5 to 10 kilometers as you go in. So, I mean, it's hard in hindsight to actually describe what was happening, but I do remember quite clearly how wild it was there. Mm-hmm. And it's also hard in hindsight to actually say, well, maybe that's an overwash zone, and then beyond that overwash zone, the waves are still capable of fracturing the ice, but they're perhaps not overwashing so much. And then as you go further in, the ice doesn't fracture and the waves are much more attenuated. That's what I'd like to say, but it does actually show in an image that I've got, or a schematic it is actually, that I did work in that outer zone. So I guess I must have been slightly crazy, or health and safety regulations were somewhat different at that time. But yeah, we did 2 stations in that edge zone where the attenuation was so rapid. And we did put accelerometers on the surface of the ice. So I can't remember whether there was overwashing in the zone, but I suspect there was. Further in, there was no overwashing. I mean, we paddled around, we walked around on the tops of floes, and I know there was no overwashing, but I'm not sure about the edge zone. So I think that really agrees with some of your modeling observations.
Yeah, I mean, this is definitely part of my thinking and our thinking on the marginalized, or this region of transition, where we have kind of this band of high frequency kind of wave effects, and then this other band of longer. Yeah.
Very nice talk.
Thank you.
Some questions. What you call the overwash is now in naval field as grain water, and also water on deck. This is for ship, and grain water, it could be also for offshore platforms. And platforms, in particular now, European Commission is interested in so-called floating solar panels. So that is kind of the mat covered with solar panels, and it's not ice. You can find it in Malta and Portugal, as I remember. So we submitted proposal. It was rejected 3 times on that. But the people working on it in the Netherlands, and there is the positive and negative sides of overwashing, because for solar panels, it's good if they are in water, because this is the temperature is getting lower, and then the more efficient. But for some cases, like with the structures on deck, it's not good, because the overwash is kind of dampering flow, and it breaks, and also many things. But there is, in addition to that, there is another phenomenon you didn't mention, but it's in one video I could observe it. It's a part of the actually edge of the plate. It exits from the water and enters it again. So you cannot find it in your linear solution, but you can find it easily in experiments. And that is definitely its a source of dissipation. But it's non-linear, right? So this is complicated, and I should apologize about my criticism of attenuation coefficient. I said nothing. No. I didn't say that it's wrong. No, I just concerned that there could be way around if we so much trying to break a wall. So there could be door somewhere there.
Exactly. No,
and
that's a good point.
We should look at that door, but not trying to make a hole in the wall.
Yeah, we shouldn't just focus in on one particular thing. Yeah. Totally. Yeah.
Hi. I was just wondering, do you have any particular conditions at the 2 edges of your plate in the one-dimensional model?
Yes, it's like the 3rd and 4th derivative go to 0 in X. So there's no bending. No shear. Yeah.
When the water is above the zero, there is discontinuity, then
Yeah. So essentially, my linear model doesn't see this, and then I feed the information from the linear model into a shallow water.
It's like wave breaking the temperature.
Yeah, kind of. Yeah. Like ideally, I guess, if you really wanted to understand the plate, maybe you could get like a linear theory and like do a box around your thing and do some kind of more complicated fluid dynamics in like a box around your flow or something.
Yeah. Also, your thin box changed shape as time went on. Is that part of the sort of approximation?
Sorry, what? You mean like in this kind of hypothetical model that we don't have yet?
That's right.
Yeah. Okay. Yeah. Then throw it all in. Yeah. It'll do it all.
Okay. Yeah. Thank you.
Maybe last question.
Thank you for a very nice talk. Just to throw a spanner in the works, over and above the effect of the wave amplitude decay as you enter the marginal ice zone, could there be effects due to flow jostling which would impact the overwash? Because the flows can be quite compact at the edge and they're moving around. They can be squeezing the water between them.
Yes.
I can imagine effects over and above what you've described so far of your theory.
Yeah, I comment on that in the Phil Trans paper because we had a very high concentration experiment. And there you can see overwashing for waves caused by the collision of flows that you can't see for waves in the low concentration, just because you don't have the flow interactions. So absolutely, yeah, it's probably more of a dominant source, I would say, maybe.
Now
I could
the
see
last
that being
question.
the case.
Just a an observation and a question. Based on Danny's point, if the picture you showed right at the beginning with the ship shows the edges of the floes raised, which does actually suggest collisions. In fact, when I first saw that, I thought, oh, that looks like pancake ice, but I guess the scale is larger than that. But it does suggest that the floes are actually buffeting together and pumping fluid onto the surface, and then that fluid is freezing. But what I was going to ask was the wave tank experiments. The effect of water depth, is that significant in terms of the ability for the flows to overwash? I mean, my gut feeling says shallower water should produce more overwash, but I don't actually know that that's true.
Yeah, I'm not sure.
And because it's a wave tank, of course, you've got all sorts of scaling issues, and it's a difficult problem to scale because you're scaling the mechanics of the flow and you're scaling the fluid dynamics. So I haven't seen a good dimensional analysis that allows me to propagate that up into the real world. And I just wondered whether the shallow water was an issue. Maybe you could look at your data to see whether there is an effect of shallowness.
It's interesting.
I don't know.
The way I think about it is mainly the more your flow conforms to the surface of your water, the less it's going to overwash, essentially. And that's kind of like a more abstract view. But I don't know how the shallowness affects that kind of interplay either. Yeah.
We have time.
Yes, I got everyone excited.
It seems that a lot of people comment about the CFD and the viscosity and the underwash on top. And Jordan should have said that Luke was involved in a paper in which they actually did the CFD, and it was published in JFM in 2020. I think it's the Nelly
paper,
yeah, Nelly Bennett's, in which they have an oversight mesh that follows the plate itself.
Yes.
And they study the dissipation mechanism.
Good point.
Thank you. So I think we should thank the speaker of this morning session again. And we have a short coffee break.